Hello from the Forcetronics YouTube channel and welcome to design tutorial for 24 volt AC to DC power supply for HVAC and industrial applications. And this is going to be part 2 in a 2-part series. Before I get started, I'll just mention check out forcetronics.com for information on our for-pay design services. And if you like what you see here, please subscribe to my channel. All right, let's get started. This is a slide I showed in part 1. It just kind of shows the design goals of the power supply. As I mentioned, I was designing boards for HVAC applications, and in HVAC applications, a lot of times you have a 24 volt AC RMS power supply or power source to power your design. So I needed to create a power supply to handle that 24 volt AC and give me a 10 or 12 volt output. And the power supply also has to be able to handle DC input as well. It needs to be electrically rugged, which we talked about in part 1. And then it also needs a small form factor and a low noise output. And those aspects we'll talk about here in part 2. And the goal here is we're going to talk about some of the PCB design aspects that we want to look out for. And we'll see some of those straight from the data sheet. Then we'll look at the PCB layout, why we did certain things. And then we'll see some test results from different stages of the power supply showing the finished working design. All right, here we're looking at the data sheet. I showed this in part 1 and I stressed how important it is to read the data sheet whenever you're working with any type of IC for the first time. But the data sheet provides a lot of guidance on PCB layout. We're not going to touch everything, but we'll touch some of the high points and we'll see how we integrate that into the design. One of the things they point out right away is the ceramic bypass capacitor on the input. They want that to be as close as possible to the VIN connector and to the power ground. And why do they want that? To reduce EMI. EMI stands for electromagnetic interference, and this is essentially electromagnetic interference that's radiating off the board. And so the reason they want this to be close to the VIN is because of these sharp current changes, DI, DT. And if you have it far away from the board, and once again, the capacitor is part of that, right? The capacitor, the DC to DC converter is going to be pulling sudden dynamic changes in voltage from the capacitor. So the capacitor is constantly charging and discharging. And the idea here is you don't want a long trace between those because that can act like an antenna and radiate some of the EMI from those transients. That's why they want it close to it. There's federal guidelines or regulations of how much EMI a power supply can have, so it's important to follow that. You can see here on the bottom they have similar requirements for the output capacitors. They talk a lot about thermal considerations, and the idea here is the DC to DC converter chip has a small form factor, but it has to dissipate a lot of heat. That's why it has that power pad, which I pointed out in part 1. And they're just saying you need to have large ground planes and vias to help dissipate heat away from the DC to DC converter chip for good thermal management. They also mention about analog ground and power ground. We'll talk about that in the layout. The idea is power ground's where the noisy stuff's supposed to happen, and analog grounds is supposed to be a little less noisy. All right, I'm skipping some of this stuff, but here they mention the feedback resistors, and they want the feedback path as well as the they want the feedback resistors to be close to the feedback pin. They don't want it to be close to Vout. And the feedback resistors, remember, they're used to set the output voltage. And the way the DC to DC converter works is the way that it adjusts its output based on changing load conditions is through the feedback loop. So that's an important area for low noise to have a accurate output on your power supply. And then they show a layout example. Remember, this is that power pad. So this is the DC to DC converter chip. This is that power pad that's on the bottom of it that helps enable TI to make chips that are really small but could handle high voltages in this case or high currents. And this is important to allow current to flow. Remember, ground is not, just something where nothing's happening. Ground is where current is flowing. It's sometimes we forget that because it covers everywhere, or especially if you have a ground plane, it's covering everywhere. But there is current flowing through ground. Also, that's where we're going to dissipate our heat. So we can see these large ground plane, it's flowing through the chip. Then they have these vias. So the chip has solder paste underneath. When it's reflowed, it's attached to this ground pad, and then they're recommending these thermal vias that connect one ground plane level to another ground plane level in the board. That allows heat then to flow through those vias to another copper layer to help further dissipate heat. Notice that they have the input capacitors. This is V-in, right? And they have a large trace there for lower resistance, right? We want as little resistance in our traces as possible because that leads to better efficiency, but it also leads to less IR loss, and IR loss generates heat. Also, having these wide traces, whether it's V-in or V-out, helps eliminate parasitic capacitance as well. Now, might help eliminate parasitic capacitance, but I meant to say inductance, right? And we don't want any stray inductance in our design, especially if we have high switching rates. Here's that feedback loop they mentioned. So you can see they mentioned something about it again. So this is V-out. This is the output path of the power, the DC out. They say V-out sense point is away from inductor and past C-out. So they're saying where you attach your trace to go to the feedback pin through our resistor dividers, they want to make sure that's after these capacitors and inductors. And that's because this is a noisy area. Your inductor has a magnetic field forming and then collapsing, forming and collapsing as the DC to DC converter switches on and off. And C-out is charging and discharging. So it's, this is almost like a filter section to smooth out that PWM signal that's coming out of the DC to DC converter. So they want the feedback loop to be away from that so it's a little lower noise. Notice that we're seeing power ground, ground, A ground. They made this a little confusing, but the idea is with a DC to DC converter, typically you have a power ground and you have a less noisy ground or analog ground. Here, I think they're using power ground and ground interchangeably, and then analog ground is supposed to be the quiet area. But things like this input capacitor where we have the current transients, as well as this inductor and output capacitance where we have, once again, current flowing on and off, they basically want to make sure that certain things can be in that noisy area and certain things they want to keep out of that noisy area. And they don't show that well here, but we'll show how we're going to kind of separate the ground a little bit to create a less noisy area for these type of pins. All right, now we're looking at WebBench Power Designer. This is TI's free web browser hosted application. This is one of the reasons I went with a TI chip, is because they make quality power ICs, they know what they're doing, and they have tools like this. And this tutorial is made for non-power electronic engineers like me who need to design some type of power supply and need tools to help them get it done. So here we're looking at the recommended PCB layout. They base this on a 4-layer board. I'm going to do it on a 2-layer board. You can see here, one of the things they're kind of cheating on is you're not going to put a design like this on a board this big. So they're able to sort of exaggerate some of their recommendations because they're using a huge board. But they have V-in, a nice wide trace for V-in. They have their input capacitors close by the input pins. They have their inductor, then they have C-out. They have the ground pad for the noisy area. They have a ground and ground 1. Yeah, I don't want to spend too much time on this. You can, generate your own. The thing I like this, though, is if you're wondering how close is close, when in the layout guidelines it doesn't specify, it should be this close and not farther than this. This is a good guide to kind of show you, all right, this can be this far away and this can be this. So it's another resource to help you with your layout. Speaking of layout, why don't we look at the layout for our design? Okay, here we're looking at Eagle CAD for doing PCB layout. I have the premium version. I paid a lot of money for it. I think they have some free versions. I'm not sure if it's just available for education purposes these days. But if you're looking for a free PCB layout platform, you can go to KiCad, which is an open source. But here we're looking at my board design. The red is the top layer or the top copper. So anything red like these, These copper pores or these traces are on the top, and these blue traces are on the bottom. These circle things are vias. They're typically represented in green, and they can go all the way through the board. And of course, we have what we do first before we do our layout. We have our schematic that we build, and I showed this in part 1. But let's focus on the actual layout portion. Here is my input. So for AC, this would sort of be the hot, and this one would be the neutral. This is the output. This would be the output DC, and this would be the ground connection. Now, I made this design to be integrated onto existing design boards. And I also made it because we had a design where we were using some off-the-shelf power supplies that were very cheap, and some of them started breaking. So we wanted to be able to integrate this in. So that's why it's a standalone design with these pads. These pads allow you to do, a through-hole type connection as well as a surface mount if you want. Oh, one thing I want to point out is this is not an isolated design. So in HVAC applications, the 24-volt AC comes from a transformer that's stepped down from line power. So it already is isolated from the main power line. Now you can get DC to DC converters that are isolated that have mini transformers built in. They're much more expensive. I didn't need that, so notice my ground is tied to the same potential as the neutral from the AC. Here on the input, notice we have a big pad here, right, for our input voltage. Then we have to go through the Schottky diode. That's our half-wave rectifier. Then we have our big hulking cap, electrolytic, and then the bypass cap that the DC to DC converter calls out. And once again, we have a big, wide trace to get to those input pins. Here we have our Zener diode. So if it's over 60 volts, the Zener diode will conduct to ground to try and pull that voltage down so we don't damage our DC to DC converter. Notice we have a fat wide trace for our ground, or we can call it power ground. So that goes all the way through here on the bottom, as well as here is our power ground. And then we have a more isolated analog ground. I'm calling it A ground. And what I do is I just connect it with this short. So it tries to keep the noisy elements. Here's our output capacitors. They're tied to power ground. Our input capacitors are tied to power ground. But here we have one of the resistors from our feedback loop. We also have another pin that they wanted tied to analog ground for a more quiet, less noisy ground plane. Of course, the IC itself is going to be tied to power ground, and we have a lot of vias in here, and these vias are connecting to the bottom layer, which is a ground plane. The datasheet recommended a lot of vias here to help to get that thermal dissipation that's coming from the power pad of the chip, and then we can dissipate it throughout the ground plane. And I can just show you by flipping the board over that this is the blue, this is the bottom ground plane. We only have one small trace, and that's the analog ground run. And the rest of this is all a ground plane. So all these vias are connecting the top power ground to this bottom power ground. So we get a nice large ground plane for current to flow and for heat to dissipate. Let me flip the design back over. All right, I mentioned these feedback. Notice the trace, this is the feedback trace. Notice it connects to after the capacitors and the inductors, so it's less quiet to monitor its output, like the data sheet recommended. I already mentioned this capacitor is close. We have the inductor close. We have big fat traces coming off of it. Once we get across the inductor, we have a big fat V-out trace with our 3 22 microfarad ceramic caps. And then right before we get to the final output, we have our ferrite bead and our output filtering cap to help reduce the noise further. So as a reminder, we did 2 things to help reduce the noise. First, we have larger output capacitors than recommended. We have 22 microfarad ones, 3 of them, which is that's like 66 microfarads. In the original design that I did on PowerBench, they only recommended like 40 microfarads. And then of course we have the ferrite bead, which I talked about in part 1, and the filter cap. And we'll see the effects of these in some of the test runs. All right, let's look at our actual design that we took from here and turned it into a real thing. All right, here's a picture of the design. Notice nice small form factor. And I have this set up just for testing. This is the input. This yellow represents what we can call hot on the AC side. and the green is the neutral. I have 25 volts AC RMS coming from an AC source. Here's an example of a measurement I'm making with a scope probe and the scope's ground connection, and then this red and black connector are the load. And I have adjustable load to draw current from the design while we're testing it, so we can test it in its working form. Here's a zoomed in picture of it. Here's our here's our Zener diode. Here's our Schottky diode that's rectifying that input AC. Here's our big electrolytic cap to help smooth out that AC, those big humps coming in. And then we have the bypass capacitor that the DC to DC converter asked for. And I mentioned in part 1 that capacitors, in my experience, tend to be the weakest link in power supply reliability. So this Zener diode, 60 volts, this power supply can handle up to 60 volts. The voltage will actually be lower, but I size these capacitors for 100 volts. So this and this is the reason this 10 microfarad cap's so big, is it can handle up to 100 volts. That was done to make them as rugged as possible, so they're operating well within their range, and hopefully we'll get a longer life out of them. Here's the capacitor and the 2 feedback resistors for setting the output voltage. Here's our feedback trace that we showed in the PCB layout. Here is that quieter ground area. See that small, I don't know if, I hope this shows well, but you can kind of see the pads, the copper pores, and this one just has that small connection, and the rest is mainly the power ground. Here's our output capacitors, our inductors. Here's our ferrite bead, and then the output filter cap. All right, and note, this is upside down than the way we were looking at it in the layout tool. So now let's look at some test results of our power supply in action. So I have an AC source powering it, and then I have a load that's pulling about 200 milliamps. And let's look at the signal of our input AC signal, and then let's look at our raw DC or our rectified AC signal that's somewhat filtered. So here is a oscilloscope screen capture. The divisions are 20 volts per division. So this is our 25 volt RMS AC signal. Notice that this is RMS. So really, the positive going hump, this is ground right here. So we have negative, and then here it goes positive. That's, above 35 volts right here. All right, so remember, this signal is going to go through this Schottky diode, which is only going to allow the positive humps to pass, and these capacitors then are going to try to smooth it out. And that's what we're seeing in this bottom signal where this arrow is pointing. So these signals were done simultaneously, so they're, time synced. They're triggering off the first signal. We can see it's 60 hertz, 25 volts, and then the bottom signal is smoothed out a little, right? All the negative components are gone because it was rectified, and then due to the capacitor charging and discharging, it's trying to smooth out this hump to make a continuous signal. Now, it's not perfect, but it's much better conditioned for the DC to DC converter to handle it. Let's show the output just so you can see that we are getting a 10 volt output. So this oscilloscope display is not too exciting, but basically here's ground down here. We're looking at 2 volts per division. So 2, 4, 6, 8, 10, and there's our level. So we're getting a clean 10 volts out, but we're going to see how clean it is by zooming in on this signal. All right. So what we did was we were just looking at the output DC level at 2 volts per division. We zoomed in at 50 millivolts per division. And the yellow, actually the one we looked on the previous slide is the green level, this arrow green pointing to the output after the ferrite bead. And then this yellow signal is after the output capacitors, but before the ferrite bead. Now, one thing I want you to note is this is normal for a DC to DC converter. You're going to have noise elements and small transients. And if you notice, I have these 2 cursors set up between these 2 large transients. They basically equal 500 kilohertz. And so that is the switching speed of the DC to DC converter, if you remember from part 1. So the point is it's basically impossible, at least today it's impossible, to totally smooth out that signal from its pulse width modulated origins coming from the DC to DC converter. The inductor and those output caps do the best they can, but you're going to still have some noise here. Now here, this transient is probably, around 125 millivolts. We see some other smaller ones mixed in. But if you look after the ferrite bead, which adds further attenuation to high frequency noise, and this filter, they actually get cut down a little. They're still there, and I did some cursors on them, so they're about, 40, 45 millivolts. And I believe the noise spec for the DC-DC converter is about 150 millivolts. So you can see we cut it down pretty far here. So this is pretty good. We're never going to have it perfect, but that's pretty low noise for a DC to DC converter. All right, before I close, I just wanted to show the BOM again. Feel free to take a screenshot if you're interested. But I think we met our goals, right? We wanted a small form factor. We wanted it to work. We wanted a rugged input that could handle DC and AC, and we wanted a fairly low noise output. So I was really happy with the outcome of this design. If you have any questions, please use the comment section. And if you think there's important aspects or points that I missed, feel free to let others know through the comment section. If you like what you saw here, please like the video or subscribe to my channel. Thank you for watching.